This is Physics 2212 Lab 4, Macroscopic View of RC and DC Circuits, presented by Kenneth Alexander Jenkins. As an introduction to today's lab, the lab explores the applications of energy conservation and current conservation principles to predict and measure the behavior of circuits with resistors in series and parallel, while also analyzing the characteristics of ohmic resistors and capacitors. The fundamental principles are Ohm's law, which is V equals IR, In equals I out, the node rule, V net equals 0, and sigma V equals 0, loop rule. As a brief result, RC experimental equals 8.6 seconds and RC calculated equals 6 seconds. Assumptions, models, and details. Definitions of systems and surroundings. The system is the circuit, and surroundings is everything else. Modeling. To lower the barrier of entry for this lab, it will be conducted online using an ideal circuit simulator. This model allows us to change the value of the resistors and capacitors on the fly. Assumption, there is no resistance in both the simulated wires and the simulated ammeter. Part 1, predictions and observations. Experiment details. Two 1.5 volt batteries and 2 ammeters and 2 resistors, one 47 ohm and the other 100 ohm, totaling 147 ohm, are connected, as seen in the diagram to the right. I equals V over R. The calculated I equals 0.02 amps. Subbing an ammeter with a voltmeter gives us volts equals 3.0 and amps equals 0. Current equals 0. This is because the circuit is now open and there's no current flowing through the wire. However, the potential difference always stays the same. Part 1, predictions and observations. As seen on the left, the calculated results are given on the left. On the right, you can see the predicted graphs. The total voltage is 0.0204 amps. Part 1, questions, answers. When you attach a voltmeter, you alter the circuit. Why doesn't the ammeter change the reading? Voltmeters have very high resistances. So in turn, you're altering the circuit every time since the circuit has very little current that can flow through the voltmeter. Ammeters do not have this problem. Connect a voltmeter across the 100 ohm resistor again. Note the ammeter reading. The current shoots up to about 0.06 amps. This is because the total resistance decreased, allowing the current to increase. Now replace the voltmeter in parallel with a 100 ohm resistor. What happens to the current flowing through the other ammeter? Why? Ammeters have very low resistance, so almost all of the current will bypass the resistor and flow through the ammeter instead. This will lower the overall resistance from 147 ohms to 47 ohms. Calculated resistance results are the resistance of the 47 ohm resistor is given right here, as well as the 100 ohm resistor, the resistance of the wire, and the resistance of the ammeter. Part 2, predictions and observations. Experiment details. One 9-volt battery, 2 light bulbs, one 10 ohm and another 20 ohm, and one 200 microfarad capacitor are connected. Connecting the 100 ohm bulb and capacitor in series begins charging the 200 microfarad capacitor. The bulb shines brightly and eventually dims out until there is no more light. Current decreases down to 0 amps. When you disconnect the battery, this begins discharging the 20 microfarad capacitor. The bulb shines bright initially and continues to dim out until there is no more light. Current will decrease down to 0 amps. Approximate timing to charge and discharge the light bulbs. 100 ohm light bulb charged and discharged in about 1.45 seconds, and the 200 ohm light bulb charged and discharged at 28 seconds. Time-dependent model. As seen here, this model was given by the lab report. This was created in Excel and imported into the spreadsheet. The time-dependent model is given by the slope. For the experimental RC, the slope is given as the RC, and it is 1 over RC. So as you can see right here, the calculated value is negative 0.1164. And then this is divided by -1, which gives us 8.6 seconds. The calculated RC is resistance times capacitance, which gives us about 6 seconds. It is important to note that the R-squared value for this figure is not very good. So as a result, I will be counting this in the end for the possible sources of error. What if and why questions? What if you're doing this lab in real life and used an actual voltmeter instead of a simulated ammeter? What's the difference with a real ammeter, and how would it have affected your circuits if you hooked it up to? In this lab, PHET, the online circuit generator, does not use ammeters that contribute resistance. In real life, all conductors contribute some form of resistance. This includes ammeters. This would have led to a slightly lower current than observed in the lab. What if you were doing this lab in real life and used a real battery to charge a capacitor with no resistor in the current? How quickly would have our ideal model predicted the capacitor to reach full charge? Would this prediction happen in real life? In simulation, full charge on the capacitor would have been reached instantly since there was no resistor to slow it down. However, in real life, it would have been slowed down by some amount since the wires have resistance. This resistance alone would have slowed down the charging enough to see a difference between the two. Potential sources of error and improvement. Potential sources of error include glitches in the p-head software, precision of the amp meter, timing errors, measurement errors, especially seen in the RC circuit since the fit value is fairly large, and improvements. Running more trials and comparing results between real circuits and simulated circuits.